All right, we're in section 39 now, and my name is Ron Bannon. This is a draft version of Webster Wells's Advanced Course in Algebra dating back to 1904. It was basically designed to get students that were wishing to enter into the STEM-related careers, science, technology, engineering, and mathematics, a good basis of entering those careers, all right? Now, what I mean by the study of those careers, which, you get through the algebra, the trigonometry, calculus, linear algebra, differential equations, abstract algebra, real analysis, complex analysis. It just doesn't stop, all right? But anyway, technique, pretty much standard. What are you going to do? Our technique of learning this stuff over here, there'll be contents. We would like you to look at that. We would like you to look at the examples and try to understand those and get busy working on those exercises to reinforce what you're learning. This document, the PDF at least, is being prepared for the Prison Mathematics Project participants only, all right? I realize some students may want access to my documents, and teachers as well, and what you're going to do is, if you wanted that, just reach out to me and let me know you're interested, and then I'll try to keep you on a list and inform you when it's going to become available, all right? I need to get some feedback on the document before I make it available, though, all right? And hopefully the feedback I'm getting is from the incarcerated individuals and their mentors, all right? So here's the deal. What are we going to be doing? We're going to be looking at the document, all right? I'm not going to read it to you. And someone says, I really have a tough time reading through or understanding what they're trying to tell me, including what I'm trying to tell you. It happens, right? You don't understand everything. It's just natural. You don't understand everybody. But the bottom line, they're going to talk about these inconsistent, indeterminate linear equations with two unknowns in it. So they start giving you examples. And if you graph those examples, what you notice is those two lines you just drew out appear to be parallel. All right? So, they get other examples. I want to point out other examples might be where the two lines actually touch each other all the time. All right? So, bottom line, Wells gives pictures, I give pictures, Wells gives pictures, so forth and so on. Another thing they talk about is graph rotational roots. What are roots? They're basically just the x-intercepts. All right? So what I want to do is I want to go through the examples. And certainly the way I do that, it might appear to be different than the way Wells would do that. All right? Now, in time, you might get better at this just by looking at the problems. I like elimination, though. I'll tell you, if I'm eliminating it, I want to concentrate on the x's. So I want to make the least common multiple between 3 and 6 is 6. So I'm going to multiply the top equation by minus 2. And what do you get? And there is a point to this. You're going to get minus 6x plus, let's see what you get over there. Minus 6x plus 4y, right? Minus 10. And what do you get over here? 6x minus 4y is equal to minus 7. Well, you know what? If I add that together, the x's definitely disappear, but so do the y's. And I get 0. And I get 0 equals minus 17. I hope you realize that if someone told you that 0 is minus 17, they're not being truthful to you. So you can say it's a good example of that this equation has no solution. Now, to me, visually, what does that mean? That means that these two lines never touch each other. All right? So what I want to claim over here, that I kind of rewrote the system for you, but you don't have to do that. What I would recommend you do is, bottom line is I would recommend graphing it. All right? I would recommend graphing it, by the way. Now, why do I recommend graphing? One is practice. Two, you're going to see that these two lines are going to be parallel. Now, I want to point out what I mean by that. If you graph these two lines out, one line's going to look like this, and the other line's going to look like this over here. Now, granted, someone says you're not doing a very accurate picture. You're right, I'm not doing an accurate picture, but your lines would look something like that over there. Right, I'm going to erase this. I didn't really graph it out. I just said if I graphed it, it looks sort of like that. So I like the technique I do with elimination. I realize the system, they never touch each other. All right, I'm going to read it to you, though. All right? So it says, the system can be rewritten. Someone says, why do you do that? Well, one thing I would do is, just for comparison purposes, if you were to write that down, and I want to write down what I mean by comparison, y equals something, y equals something. So if you would compare those two, I would say 3 halves of an x minus 5 halves is being compared to, because, y equals y, right? 3 halves of an x plus 7 quarters. Well, you know what? I'm left in the same conundrum. If I subtract 3 halves x from both sides, I'm left with this. And this can't be true. These will never be equal. They're never touching each other. But again, graph it out, you'll see that. Let me erase that. That's just me talking through what I'm looking at. And I'll continue to read. You should note that these two lines could never share a point in common. Hence, they are parallel lines that never intersect. The given equations are called inconsistent. And I want to outline that for you. That's a big word that we use in mathematics. Inconsistent. And we shall always find that two inconsistent equations with two unknown numbers are represented by parallel lines. When I say parallel graphs, parallel lines, the bottom line is they're parallel lines that never intersect. Let's look at the next one. And again, I'm not giving you a graph, but I'll talk about the graphing technique in a second. I like elimination. And what am I going to do over here? I'm looking at it, and again, I'm going to eliminate x again. Oops, sorry about that. Get back my pen. And my pen back. So I'm going to say the LCM between 3 and 6. Again, I'm trying to get rid of the x's. I'm going to say it's 6, so I'm going to do minus 2 times the top. And let's see what you get. So you would get minus 6x plus 4y equals minus 10. That's not so bad. Second equation, 6x minus 4y equals 10. If you add those together, what do you get? 0 equals 0. Well, I hope you realize that 0 equals 0 is always true. So I'm trying to think about it. If they're always true, that means these two lines are always touching each other. They intersect everywhere. They're everywhere intersecting. They have all points in common. All right? So what do? You could graph it if you want. If you graph this out, again, I want to point out, if you graph it out, there'd be a y-axis, there'd be an x-axis, and the graphs, I say, sort of like this. That's one line. That's one line. And then if you did the other line, it's going to lie right on top of this one over here. They intersect everywhere. All right? So what did I do over here? I want to point out what I did. I rewrote the system. Why do I rewrite the system? I solve for y. A lot of students will do this. Once you do that, you should start to realize that you get something what's known as an identity. That 3 halves, whoops, sorry about that. That 3 halves of an x minus 5 halves, that's this y, is identical to 3 halves of an x minus 5 halves. And that's true for all x. Every single x in the universe, that's going to work out. So if you were to write down all the points that these have in common, the general way we do it is we say any x and the y would always be related to the x by this relationship over here. So 3 halves of an x minus 5. And that's the ordered pair of solution to that. No matter what x you give me, you come out to y. For example, if x is 0, you'd get the 0.5. If x is 2, you may wonder why I'm choosing 2 because it's easy. That would be 3 minus 5, which would be minus 2. If you choose x to be 4, I'm only picking easy numbers. What would you get? Let's see. 4 would give you 6 minus 5 is 1, so forth and so on. You could do this all day long. There's an infinite number of points in common, and those points are of the form x comma 3 half x minus 5. I'm sorry, that's 5 halves. I made a mistake. I misspoke, and I got to go back and do it again. These are not correct. Sorry about that. What do you get over here? If you chose x to be 0, what would you get? Minus 5 halves. If you chose x to be 2, again, I'm picking easy points, you would get 6 minus 5, which is 1 half. If you chose x to be 4, you would get, let me make sure I did that right, by the way. 2 times 3 is 6. Yeah, 4. 4 times 3 would be, you know what, I picked 3 instead. That's getting too bad. Let's go with the 4. 4 times 3 is 12. 12 minus 5 is 7, so 7 halves. All right, so my goal here is, bottom line is, graph it. You'll see that. You'll see they're lying on top of each other. Let me just read this through to you. And why do I read it to you? We really want you guys to read. But anyway, let me read it to you. Two equations these two equations are exactly the same. That is, they coincide. They're going to use a word that's used in mathematics. It's called dependent. Why do we say they're dependent? They're the same thing, just like you depend on yourself. The parallel lines that always intersect. They are parallel, they always intersect. All right, we also say they're coincident. They're on top of each other. And we shall always find that two dependent equations with two unknown numbers are represented by parallel lines that coincide. The point can be represented as an ordered pair by setting x equals to a. I want to point out the same thing over here. So if x is a, what would you get over here? Well, if x is a, you get 3/2 of an a minus 5/2. No big deal there. All right, let's take a look at number 3. And number 3 has something that, just adding to the what we discussed in the past, says as an aid to graphing, we often use 2 points, the x-intercept or the root, and the y-intercept. What's the x-intercept? Well, we did mention this before. It's a point which the graph or the line crosses the x-axis. The x-intercept, the y-coordinate is 0. We've talked about that before. We set y to be 0. So it even says that, set y to be 0 and solve for x. What's the y-intercept? It's a point where the line crosses the y-axis. The y-intercept, the x-coordinate is 0. We've talked about that before. To find the y-intercept, what do? You set x to be 0 and solve for y. All right, let's talk about this one over here. And let's see if we can do what they want us to do. All right, find the x-intercept and y-intercept. How do I do that? Well, let's write this down. X-intercept. All you have to do is set y equal to 0. Well, that should be easy. What do you get? You get 5x equals 7, or x equals 7/5. So let's write down the x-intercept now. That's going to be 7/5, comma 0. If you want a mixed number, it goes in 1 time, 1 2/5, comma 0. All right? Let's do the y-intercept. How do you do that? Set x equal to 0. Let's do that. What do you get? 2y is 7. And that looks pretty easy to do, by the way. What do you get? You get y equals 7/2. So what do you get? X is 0. The y is 7 over 2. 0, 2 goes into 7 3 times with the remainder of 1. So 3.5. All right, these answers are listed for you. And for a reason, we want you to look at the k. I got this answer here. This is the x-intercept. And I got the y-intercept over here. Now, what makes these points nice for some students, they're not bad to plot. All right, let me just go through that real quick with you. And again, I'm just doing a ballpark picture, not a very good picture. Let me plot this point over here. That's going to be 0, comma 3.5. What does that mean? Well, I go up 1, 2, 3. If this is 4, 3.5 is about here. And this one over here is 1 2/5. So that's going to be 1, and that's going to be 2. So 1 2/5 is about here. All right, what do you do now? Draw a line through it. And that's our line over there. All right, so I'm going to say, for the most part, it's not a bad section. You learned a lot in a section, though. You learned something about graphing. It's useful, so you have a visual understanding of what's going on. But what you need to start doing now is you need to seriously think about reinforcing what was discussed. All right, so you want to do the exercises. So, do number 1, do number 2, do number 3. Please try to think about these things, by the way. We also recommend reading the answer key. 5. I really do mean that. Don't blow this off and say it's not important. It's important. Each block you put down is an important block. Eventually you get to the SAGE business. SAGE is a computer algebra system, or a CAS. Go to this website. You'll get a freely available download of it, or the interactive web-based application. And you may want to try to do the code. All right? What's the code about? The code is about solving systems of equations. It's about these things that don't intersect at one spot, or intersect at an infinite number of spots. All right? So look at it. If you have any questions or concern, though, you need to reach out to me. My name, again, is Bannon. My email address is Bannon. That's B as in boy, the @ symbol, NNON.US. Okay? I'm looking forward to hearing from people that down to errors in the document. Again, we would really love to have the document improve over time. And the only way it's going to improve over time is if people feed back to me. That's what's going to make it improve. Thank you so much.